We're going to switch gears a little bit now, and I'm going to talk about cryptography for blockchains. Okay, so I'll talk a little bit about some recent work we've been doing that's been motivated by some newly coming projects in the space. So I guess I wanted to start with just an overview, a very, very brief overview. I have a whole segment that I actually took out just on what blockchains are, where they're going, why they're useful, why is there so much interest in them now. But I think you guys already know that. So I'll just tell you kind of why I'm excited about them. And for me, it's just technically really interesting. Yeah, so blockchains just pose a whole bunch of new questions that are really fun to think about. And it's like an endless stream of problems for us to kind of solve, and because it really does lead to new technology. Yeah, so building these decentralized systems is just technically difficult. And so, there's needs for better consensus protocols. These are basically questions in distributed systems. How do we make sure that everybody's looking at the same data on the blockchain? There's a need for new programming languages for these smart contracts. In fact, in our blockchain class, we teach the students this language Solidity, which is what smart contracts are written in. And I can tell you it's actually quite difficult to write contracts in Solidity that don't have security vulnerabilities. Yeah, so there's a need for better programming languages for smart contracts, and these are things that we're working on. There's a need for verification tools. How do we know that smart contracts, once you've written and deployed them, how do we know that they actually do what you expect them to do? Yeah, so there's a need for verification tools. Of course, my interest is new cryptography for blockchains. There's a whole bunch of questions on mechanism design. How do you share revenues with people when these mechanisms are deployed? So there are lots of fascinating questions there. Maybe I can just mention one. For example, if you have a pool of people who are mining a blockchain together, how do you reward each person for the fraction of the work that they did in creating a new block? Yeah, you can't just award the winner. You have to somehow split the rewards, and it's not obvious what the right mechanism there is. And of course, there's a whole host of new legal questions around blockchains. There's a whole, I don't know if you guys are aware of this, but there's a whole legal community that popped up around this area, just trying to understand the tax implications and generally what does this new type of asset actually mean. It's really kind of fascinating just from its own right. Is it a security? Is it a commodity? It's lots of debates about that. Okay, good. But in this talk, I'm just going to talk about the crypto that we're working on. And I should say, though, that because of this, as you can see, this is kind of a very far-reaching set of topics. In fact, it's not just even computer science topics. It cuts across the entire campus. And it turned out there were actually lots of people on campus starting to work on blockchains. And as a result, we created this new center. It's called the Center for Blockchain Research at Stanford, so CBR. And it's funded by some of the leading projects in the space. And we run a lot of events, as I said. If you want to learn more about CBR, please go to cbr.stanford.edu. All of our researchers up there, the faculty that's working in the space are up there. If you want to reach out to us, if you have interesting problems for us to think about, that's exactly what we're here for. The center itself runs a lot of events. Like I said, there's a whole class that we teach now on blockchains. I can tell you that attendance in the class goes up and down with the price of Bitcoin. Yes, so that's kind of interesting in its own right. As I said, we run this Stanford Blockchain Conference, which is a lot of fun. And then we also have a monthly CBR seminar. There's a mailing list you can join. Again, it's a very, very low volume mailing list, only about blockchain events on campus. So if you're interested in that, you can go ahead and join that as well and learn about some of the activities here. Okay, but I want to tell you about our latest research. So let's switch gears and talk about some crypto for blockchains. So the topic I want to tell you about is a recent paper that we wrote on this question of how to do airdrops. Yeah, so I'll talk about what airdrops are, and I'll tell you this is joint work actually with the Handshake project. So Handshake came to us with this really beautiful, fascinating questions that we started working on, and it's joint work with my student Riyad Wabi, and it's based on work with my other students, Benedict and Ben. Ben is going to talk about this more general work later towards the end of the day. So Ben will talk about how to compress the entire blockchain into a single hash value rather than keeping the huge blockchain out as it is today. All right, but today I want to talk about airdrops. Okay, in the little time that I have, let's see how much we can go through. All right, so what is an airdrop? So airdrop is basically a way to start sort of a new blockchain project. Yeah? So you want to get people to use your so Handshake, for example, was deploying a new blockchain specifically for the purpose of registering domain names. Yeah, so that you would record who owns which domain name on a public ledger, and everyone can tell who owns what. Yeah, so. Part of running a blockchain is this concept of a token that actually pays for the people who actually manage the chain, and there's somewhat of a way to kickstart a token by basically doing an airdrop to a large population, just giving everybody tokens so that they can then start, I guess, exchanging and using those tokens. Yeah, so I was interested in the mechanics of an airdrop. How do airdrops actually work? Okay, so effectively what happens is there's a sender, presumably that's the entity that's actually launching the blockchain, and this entity wants to send essentially one token to every member of a certain community. I'll denote the community by P, and the goal is one token per member. I can tell you that in fact there's some thinking out there that, gee, wouldn't it be kind of interesting if we could do an airdrop to the entire planet, right? So every person, just because you're a living person today, you would get one token, and that would be kind of an interesting social experiment. So there's even talks about doing these massive airdrops. But so far, for here today, let's just talk about airdrops to a small community. Well, not necessarily small, but it's kind of a limited community, which I'll denote by P. Okay, so the idea is that the sender is going to post all this at the beginning of time. The sender is going to post all this airdrop data to the blockchain, and the total amount that's actually airdropped is fixed at the beginning of time. So this is not a continuous process. It's because otherwise that would inflate the currency, right? So the idea is you devote a certain number of tokens to the airdrop. You do the airdrop, and then you go away. Yeah, and then people can kind of withdraw the tokens that they were given, which is kind of the next step. Every member can choose. You don't have to withdraw the token. You can just let the airdrop go. But if you are a member of the community, you can withdraw the token and then do whatever you want with it. The point is the way you withdraw it, or the way you claim it, is by posting a transaction that basically moves the token from the airdrop system, or from the airdrop list, to an address that you control. Okay, that's kind of the idea behind the mechanics of how airdrops work. So what does it mean for an airdrop? Yeah, so far so good? Yes, so we do this massive airdrop one time and one time only, and then anyone who received the token can come in and claim the token that was given to them. But of course, you don't have to. You can just let the airdrop go, and then usually there's a time bound. You're only allowed to get the token within 2 years or so. So if you don't claim it within 2 years, the token just disappears, and that's fine. Okay, so what are the security properties for an airdrop system? So first of all, we want to make sure that every user cannot claim more than one token, right? You can only claim it once. And the point is that no one can claim the token that was intended for you, not even the sender who created the airdrop system in the first place. Okay, so not even the people who created the blockchain should be able to take the money the tokens that they distribute as an airdrop, because that would just be a way for them to reward tokens to themselves. Yeah, so those are kind of the requirements. So you scratch your head for a minute and you say, wait a minute, so what about Sybil attacks, right? So what if I register, the same user registers multiple times with the community? What about, how do you know that the person who created the blockchain is not registering fake identities, and so on? So all this clearly means that we need some sort of an identity system, right? So every user in the community, we need communities where there's already a strong sense of identity. Yeah, so every user in the community should already have a certified signing key, and that signing key could be used to claim the tokens that are sent to members of the community. Okay, so we need to look for communities out there that already have these credentials that can be used to claim tokens. So what are communities like that? Well, so you can think a little bit about what are communities that already have a notion of identity and signing keys. Well, actually, before I tell you that, let's just talk about a few more properties that I want the system to satisfy. So another property is that basically another thing that could go wrong is that the person who creates the airdrop might create a bogus airdrop, right? They might actually claim, hey, we're very generous, we're giving 1 million tokens to these community members, but in reality, what they actually post is just garbage. right? So that the tokens can't actually be claimed. Or maybe they want to only reward some members of the community, but not others, even though they claim they're rewarding everybody. Yeah, so we'd like to say that if for some reason the token for a particular user is malformed, that user can actually prove that the token was malformed. Yeah, so there was some misbehavior happening, and so that's kind of an important property. And then the property that got me interested is this privacy requirement. So that was a really interesting property that they wanted to enforce, which is to say that if you're a member of the community and you claim a token, the naive thing to do is that you claim it publicly. Everybody knows that you claimed that token. It turns out that could be detrimental to actually people claiming tokens. Maybe there's some stigma associated with claiming a token or not. And so it was really important for this project that the airdrop system that they use actually maintain privacy, which is kind of where the crypto kind of gets interesting, right? So you should be able to claim a token without anyone knowing that it was you who claimed that token. Yeah, that's kind of what got me excited about this question, and that's why we started working on this. So what are some example communities where there's already an existing identity? Yeah, so one classic example is the GitHub community, right? So GitHub, already a lot of the developers, first of all, this is a good community to airdrop to because these are developers, right? So if you want people developing for your blockchain, kind of makes sense to incentivize them to go ahead and do that via an airdrop. And the interesting thing about GitHub is that most users actually set up these SSH keys to log into GitHub, right? So this is kind of remarkable. We have a community of hundreds of thousands, if not millions of people who already have public keys, and they protect those public keys, almost with their life, because your GitHub identity is kind of, tied to all the projects that you've written that you ever contributed to. So you really want to protect your GitHub identity. And so the question is, can we do an airdrop to GitHub public keys? It's kind of a pretty interesting idea, right? Right. So we like to do this airdrop to GitHub public keys, and yet GitHub users who claim their tokens can do it without revealing to the world that they actually did it. So one thing that's interesting in GitHub is you can actually set up these are SSH or PGP credentials. So GitHub supports both RSA and DSA and ECDSA credentials, but it turns out most users just use the default, which is RSA. Yeah, so most RSA credentials most credentials that people use to log into GitHub are simply RSA keys. So somehow we have to support a private airdrop where people's credentials are bound to their RSA keys, and the RSA keys themselves are public. This is, by the way, kind of another amazing thing, is that GitHub actually exposes an API that lets you read everybody's public keys. Yeah, and the reason they do that is if you want to know somebody's public key, you can just ask GitHub, what's the person's public key, and they'll tell you. Okay, good. So now we have a list of public keys, and we know that people actually guard and protect those secret keys. So it's kind of a list of certified public keys. There are other communities that also have certified public keys, but GitHub is the one that kind of seems the most interesting in this context. Okay, so the question is, how do we do this airdrop? So let's define airdrop more precisely. So we're going to have some signature scheme that people actually use to use their credentials. So like I was saying, in GitHub, the signature scheme is just going to be RSA signatures. But it could be ECDSA, could be BLS, there could be other signature schemes that we support. But like I said, we'll focus on RSA signatures. So members of the community have these public keys. Yeah, so they have public keys for this signature scheme. And the sender actually knows all these public keys. Yeah, so there's now a list of active GitHub users that contains the public keys of all active GitHub users. Yeah, turns out there's about 500,000 of them. So that's kind of the target of the airdrop. Yeah, so the sender has all these end public keys. So now an airdrop system is made up of these three algorithms. Yeah, there's a send, a claim, and a verify algorithm. So the send algorithm is what you use to actually send the token to a particular public key. Yeah, so you run send on a public key, and it gives you a public value to post on a blockchain. This is the value C. And it gives you a secret value that you need to communicate securely somehow to the recipient of the airdrop. Okay, so technically what you would do if there are n public keys in a system, you want to airdrop to n users, you would run the send algorithm n times. You would obtain these n tokens. These just get posted on the blockchain in some permuted order. And then you obtain a corresponding set of n secrets, and you have to give each one of the secrets to each one of the recipients. All right? So typically the way you would do that is you would encrypt the secrets under that public key, you would encrypt it for that user under that user's public key and post that result to the blockchain. All right, so that's how that's how you set up the airdrop to begin with. So just to make sure it's clear, what actually gets posted to the blockchain is the following two lists. Yeah, so there's one list of tokens which is randomly permuted. So on this list, you have no idea which token belongs to which user. Right? So we just publish 1 million tokens or 500,000 tokens, but you have no idea which token belongs to who. They're permuted somehow. And then separately, there's a list of encrypted secrets. Yeah, these are the secrets that are needed to withdraw the tokens. And the secrets themselves, they're actually bound to the user IDs. Yeah, so there's, again, 500,000 encrypted secrets published, but every user can just say, oh, my UID is the 5th UID on the list, so I know that this fifth element is mine. Right? So every user can easily find his encrypted secret, but the tokens, nobody knows which token belongs to who. Yeah, I hope that's clear. So the public knows which encrypted secret belongs to which user, but the public doesn't know which token belongs to which user. All right, so that's kind of what gets posted on the blockchain. And then when you come to claim a token, what you would do is basically you would use your GitHub credentials, say, you would use your private secret key, you would use the token that's been allocated to you, you would use the secret that was allocated to you, you would decrypt the encrypted secret, and recover this value S. Yeah, so you have C, S, your secret key. You have a message that says what to do with a token, so this moves it to an address that you control, and this claim algorithm will generate a certain signature that says, yes, I'm allowed to withdraw that token, and you should move it to whatever the message says that you should move it to. Yeah, so this is basically how the user claims his own token. Basically, he uses his long-term secret key and the airdrop secret that was sent to that user. So again, what gets posted is this transaction that contains C, the message, and the signature. And our goal is to make it so that A, only the user can claim his own token, and he can only claim it once. And B, that this transaction that gets posted on a blockchain reveals nothing about which public key claimed the token. That's the privacy property. Okay, so you can claim a token without telling anyone that you actually claimed it. And of course, then there's a verification algorithm. This is basically the people who run the blockchain can verify that this value sigma is correct. And if it's correct, they post it on the blockchain. Otherwise, they drop it on the floor. So far, so good? So that's what an airdrop system is. So there's a whole bunch of security properties. Maybe I can go through those quickly. So it needs to be anonymous. Again, this is very informal. It needs to be anonymous in the sense that the transaction has revealed nothing about the public key. There's, for the cryptographers in the audience, this is a simulation-based definition that says nothing is revealed. There's these unforgeability and orthogonality properties. So let me just quickly explain what that means. So unforgeability means literally that no one can take your token. Yeah, you're the only one who can create a token. Who can claim a token, even if there's a lot of information that you already see. So because remember, the user is also logging into GitHub in parallel to this whole system. So you have to make sure that the SSH logins into GitHub don't compromise that user's token. Yeah, and so that's one of the requirements. And the other requirement is that claiming the token would not compromise your credentials to GitHub. That's the orthogonality property. Yeah, so the two are sort of independent from one another. Yeah, so no one can take your token even if they listen to your GitHub logins, and nobody can log into GitHub as you, even if they can look at your the claims for your token. So the two are sort of independent. Those are the two security requirements, and that's kind of what I wrote down here. Okay, so now let's look at some constructions. Yeah, so is it clear? We're trying to construct this airdrop system, private airdrop system. So the question is just how to do it now. So it turns out if you're using ECDSA signatures, this is like trivial. There's like really almost no work for us to do. So let me explain how this works with ECDSA. You don't need to know ECDSA to see how the airdrop would work. Yeah. So all you need to know is that in ECDSA, there's a secret value which we'll call X, and there's a public value which we'll call G to the X. Yeah, you take literally some number G and you raise it to the power of X. Okay, good. Well, it's more complicated than just raising to a power, but you can think of it as raising to a power. All right, so the way we send to a public key, what we do is we just blind this public key. Yeah, so what we'll do is we'll choose a random value S. The token that gets posted on the blockchain is basically kind of this your value x blinded by this value s. Yeah, so we post g to the x plus s to the blockchain. Yeah, so c gets posted to the blockchain, and the blinding value is the secret that's sent to you privately. Yeah, sorry, I can't give a talk without doing a little bit of math. Yeah, this just goes against my nature. So there. So check mark. All right. Good. So yeah, so we basically created a new public key. We posted that public key to the chain, and this blinding value is the thing that's secretly sent to the user. The way the user claims the token now is really simple. Basically, all he does is he just signs a message using this x plus s, using this new ECDSA public key, g to the x plus s. All right, so that's all you have to do. You just blind the public key, and then sign relative to this blind public key. And the point is that signing under this public key reveals nothing about who you are, but you're the only one who knows the secret because you're the only one who has X, and you're the only one who has S. Yeah, so you're the only one who can sign on behalf of this public key, and no one else can. You notice not even the people who set up that airdrop can sign on your behalf because they don't know your long-term secret X, they just know S. Yeah, so you're the only one who knows X plus S. Okay, so that's how you would do an airdrop using ECDSA, but that doesn't quite solve our problem. If you remember, I told you that most users, like 90% of users, use RSA for their credentials, not ECDSA. So with ECDSA, this is simple. With RSA, this turns out to be much, much, much harder. Yeah, so with RSA, the question is, how do I sign using an RSA public key without revealing which public key I signed with? Yeah, that's kind of where the difficulty is. And so for this, we needed a whole new system. And in fact, most of our paper deals with this RSA mechanism, which is, how do we do private airdrops to RSA public keys? But amazingly, this is actually possible, and it's actually quite efficient. Yeah, so I'll just tell you the idea in 1 second. So in RSA, the public key is a product of two primes, p times q, and you can think of the secret key as the factorization of n. Yeah, so the secret key is like p and q. So what you do is basically when you set up the airdrop, the way you send to a particular RSA public key is you sort of commit to this RSA public key. This is what's called the Pedersen commitment of the RSA public key. So the commitment by itself reveals nothing about what the key is. And then when you want to actually withdraw the keys, claim the token, what you do is, this is kind of where all the work went, is you give an efficient zero knowledge proof that you actually know the factorization of the value that's committed in the commitment. Yeah, so you have a commitment to a value n. Nobody knows what n is, but you can give, the way you claim it is you prove that you know the factorization of whatever value was embedded inside of the commitment. All right? That's basically how you claim your token. And I'm not going to give any more details than that. That's like I said, that's the bulk of the paper, but I'm going to leave it at that. And the point is, because this is a zero knowledge proof, again, this claim transaction reveals nothing about what the public key is. Only the person who has a secret key can claim. Yeah, someone who doesn't have the secret key, including the people who set up the airdrop, can't do a claim on behalf of the user. And as I said, it has all the unforgeability properties that you would want. All right, so we can do this even for an RSA airdrop. So the scheme is a little I don't know. It takes a bit of it's a little complicated to write down. But it turns out it's actually not, when you implement it, and Riyadh actually implemented it beautifully. It actually works quite well. So here is the comparison. So you can see that kind of building the claim itself, creating the airdrop. It takes a little bit longer than an RSA signature, but not that much longer. Verifying that the claim, this is from when the user wants to claim his token. It's kind of comparable to an RSA signature. Verifying the claim, this is something that the blockchain has to do. This is something that has to be really fast because miners do this all the time. People who want to verify the blockchain later on have to do this, so this step has to be quite fast. You can see it's actually considerably slower than RSA signatures, but still only 2 milliseconds. 2 milliseconds is something that can still be supported in the real world, so it's still sufficiently fast for this to be used. Yeah, so this is, code is available basically on GitHub. Essentially, any project, what? Oh, this is implemented in C, and this is just on, I mean, this is why I wrote the numbers for comparison. Otherwise, the numbers don't mean anything. But this is just on a laptop. It's not a fancy machine. Okay, good. So yeah, so this is the code is all public. So any project that wants to create an airdrop in the future can just use this mechanism for their airdrop. It's already deployed in the Handshake protocol, and so this is, by the way, why this space is so much fun. In that you design something and then it actually gets implemented and used in the real world. So that's another reason why I kind of like working in this space. Okay, good. So I'll wrap up. I'll tell you that one last issue that we were worried about is what happens if the airdrop itself is malformed, right? If you have a dishonest sender that's claiming to do an airdrop but actually just provides garbage, so no one can claim those tokens. And it turns out there's a cute mechanism that allows us to detect this behavior. So it works as follows. So remember, these are the two lists that get posted, right? You can see the permuted tokens and the encrypted secrets. This is what gets posted on a blockchain. What we can do, in addition, is publish another unpermuted set of tokens. So here, you can see that each token actually belongs to a particular user, and you can see which token belongs to which user. So then if the user wants to complain, what they can say is, look, C1, say, belongs to user number 1, yeah? So user number 1 says, C1 was malformed. What they can do is they can actually, because they know that C1 belongs to them, and their UID is written right here, right? It's just literally written on the chain. What they can do is they can say, they can sort of open these three values and say, look, these three values are malformed, so clearly this airdrop was a malform or excluded me from getting my token. Yeah, the problem, of course, is you can't leave things like this because now you would lose all privacy because C1 is bound to the user. So what we would do is we would add a secure shuffle mechanism to this. A secure shuffle is a way for the person creating the airdrop to permute all the tokens in a way that no one can tell what the permutation is, but the airdrop creator can prove that this is really a permutation. Yeah, so a secure shuffle is needed here as well. You're shuffling these tokens and re-randomizing them. So now all of a sudden nobody knows where C1 went. So when C1 is claimed, nobody actually knows who claimed C1. But it's guaranteed that the tokens were now all created correctly. Yeah, so we can even ensure that the airdrop was done properly. All right, good. So I think I'll wrap up. There are some practical details which I think I'll ignore, and I will stop here. Okay, so thank you very much. And yeah, we have time for a few questions. Yeah, this is a bit of a quick tour. Yes? What's the GitHub repo? Oh my God, yeah. Boy, ask me offline. I don't remember the name. Yeah, I will. It's easy enough to find. Actually, you can look up our paper too, and it's in the paper. Good question. Sorry, I should have put that on the slide. Yeah, cool. All right. Well, so thanks, and you can see that I don't know this space. Maybe I'll just be philosophical for 1 second. I can tell you that on the internet, deploying new crypto protocols and new crypto mechanisms is extremely difficult, right? The crypto on the internet is sort of already ossified. It's very, very difficult to make changes. Whereas in this world, it's like this space moves so quickly that it's a wonderful playground for new crypto techniques, new crypto protocols, and new crypto mechanisms. That it's kind of a breath of fresh air, and it's a really wonderful way to get things deployed. And that's kind of part of the reason why it's so much fun to work on these problems.